We have three goals in our lesson today. First, to be able to change an exponent to a log and then a log to an exponent. Second, to find the domain of logarithmic functions. And third, and most importantly, be able to graph and then solve logarithmic equations. You should have learned last year in Algebra 2 that the whole point of logarithmic functions is to be able to solve for exponents and find exponents. So it's absolutely critical that you can change a log to an exponent and an exponent equation to a log equation to be able to solve it. So we have the definition of a log read as y equals log base a of x if and only if x is equal to a to the y power. Now remember, in an exponent, a is considered to be the base, and likewise in a logarithmic function, when we read it, we say log base a, so that number should correspond with the base in the exponent. And then if you remember from last year, we said the whole point of logs is to be able to solve for exponents. So the answer to a log is an exponent, so our y is the exponent when we change it to an exponential equation. So it would be base a raised to the y power. And we read a log as log base a of x equals y, and y being the exponent. Now there are two logs that we will use frequently as we go through the year. Both are on your calculator. When you look at the log button on your calculator, that has to do with this common log here, which is the log that has a base of 10. So it's understood that if you see just a log with no subscript in it, then it's understood to be base 10. So we would read this common log of x is equal to y, or we can think of it as log base 10 of x is equal to y, since the base is 10. Our second one, we talked about our natural base yesterday, is the natural log, and the natural log is a log base e. So when we read this, we would say natural log of x, or we could read it as log base e of x, since the base is the natural base e. So let's do a couple examples. The first one we have, write 5 squared equals 25 as a log. So if we think about our definition, we know that the base is 5, so it'll be log base 5 of 25 is equal to the exponent, which is 2. And if we go the other way, if we go from the log to an exponent, we have y equals log base 5 of x. So what's the base? The base is 5. What's the exponent? The answer to the log is equal to x. Let's do a couple examples solving log and exponential equations by switching them back and forth using the definition. So on this first one, we have log base 1.2 of m is equal to 3. So if we're going to solve that, the first thing we would do is change it to an exponent. So it'll be base 1.2 raised to the third power is equal to m. And if we take 1.2 and we raise it to the third power on our calculator, we will get approximately 1.728. That's rounded to 3 decimals. On the second example, the base is e. So we would want to use the natural log, which we write ln, of 9 equals the exponent b. So again, on our calculator, there's a button that has just ln, which is the natural log, and we would take the natural log of 9 on our calculator. Rounded to 3 decimals is 2.197. For number 3, the base is 10, so we would use the common log to find that. And we go common log of 14.5 is equal to x, which is then approximately 1.161 rounded to 3 decimals. On this fourth one, we don't know the base. Okay, so when we take a to the fourth power equals 24, in order to find the base, we would have to take the fourth root of both sides, and the fourth root of 24 would be the exact answer. Approximated would be approximately 2.213 rounded to 3 decimals. On the second one, there's a couple ways we can do this problem. If you recall in Algebra 2, you learned a formula called the change of base formula, and you could change the base of that to find the answer. A second way is you can actually take log base 2 of 8. But when you think about it, you should think of it this way. You should think of it as 2 to what power is going to give you 8. And we know, of course, that that power is 3. 2 cubed is equal to 8. Likewise, on number 6, we could solve it in each of those same ways. But the way we should think about it is x is an exponent. So 5 to what power gives you 25? And that would be 5 to the second power gives you 25. Okay, after doing these problems, you should be able to now do problems 1 through 15 on MyMathLab without any problems. If you want to pause the video from here and try those problems on MyMathLab, 1 through 15. A couple days ago, we learned how to find the inverse of functions. And you'll notice today that logs and exponential functions are essentially inverses of one another. So if we take the function f of x equals log base a of x, and we want to find the inverse of that, we would interchange the x's and y's to start and then solve for y. So we would have x is equal to log base a of y. Now, how do you solve a log? You solve a log by switching it to an exponent. So if we change that back to exponential form, that would be a to the x power is equal to y. Y representing, obviously now solved for y, representing my inverse. So the inverse of my original f of x function is, or my original log function, excuse me, is an exponential function. And we know that from the definition of an inverse that the domain of our original function, okay, which was our x values in our log, has now become the range in our inverse function. Our next goal we're going to accomplish is being able to determine the domain of a log. If you recall when we did the definition of logs, log base a of x means that a to the y is equal to x, switching it to an exponential form. And in our definition, a has to be greater than 0. So if we take any number greater than 0 and we raise it to an exponent, obviously that number is going to have to be greater than 0. So if we want to find the domain of a logarithmic function, we're essentially going to take that of part of the log and set it greater than 0 and solve. The range could be anything. We could let the exponent be negative exponents. If you recall from the other day, we could have negative exponents. We could have fractional exponents. So that could be any real number. But the domain is restricted to just being positive numbers. So if we look at that first one, y equals log base 2 of 1 minus x, we can find the domain of that by taking 1 minus x and setting it greater than 0 and solving for x. First step, obviously subtracting 1, we get negative x is greater than negative 1, multiply by negative 1, so we switch the inequality sign around, and we get x is less than 1 for the domain. So any number we plug in here, less than 1 would give us a positive number here, which by our definition of a log we have to have there. If we look at number 2, we have log base 5 of a rational function. So if we're solving that and setting that greater than 0 to start, how do you solve a inequality that's a rational inequality? Well, if you recall our steps, we need to determine what the critical numbers are. And what are the critical numbers? The critical numbers would be the x-intercepts, if there are any, and the vertical asymptote, if there is one. So if we look at this function, if we find the x-intercept will be negative 1. The vertical asymptote would be x equals 1. And then we can either do test points on each side of those, or we can draw a sketch of the graph. If we draw a sketch of the graph, we'll see that the graph has a vertical asymptote at 1. It is going to cross, has a horizontal asymptote if we want to draw that in, at y equals negative 1. It's going to cross the x-axis at negative 1 and then get infinitely close to the vertical asymptote at positive 1. So if we're looking at where is this function greater than 0, we see that the function is greater than 0 from there to there. So if we write that in interval notation, that would be from -1 to 1. If we want to write that in set notation, x would have to be greater than -1 and less than 1. For the second one, if we look at the absolute value of x having to be greater than 0, well, obviously the absolute value means the distance from 0. The distance from 0 is all real numbers, so any number you pick there is going to be greater than 0, so it'd be all real numbers except 0. Obviously, if we plug in 0 there, that's not greater than 0. That would be equal to 0. So we could write it like that. I would not do interval notation on this one, although some of you I know will. I would write it in one of those two ways. I'd either say x such that x is not equal to 0, or all real numbers except for 0. The last example we're going to look at is log base 3 of x squared plus 2x minus 3. So we have a polynomial for our of part of the log. So if we set that greater than 0, again, if you remember our steps for solving quadratic inequalities, we need to determine what the critical numbers are, and we could do that by finding what the intersection points are on the x-axis by setting it equal to 0. And if we set it equal to 0 and factor, we'll find that x is equal to -3 and +1 for my two x-intercepts. If I draw a sketch of that graph, crossing at 1 and -3, where is the graph greater than 0? Obviously, it's greater than 0 there and there. So if I put that in set notation, that would be x is less than -3 or x is greater than 1. Those of you who like interval notation could have done -infinity to -3 union 1 to infinity. The last thing we're going to do today is work with graphing logarithmic functions. The graph of logarithmic functions will have a vertical asymptote at x equals 0. If we want to change it to an exponent, that might be easier for us to think about it. This is our common log, so it'd be log base 10 raised to the y power is equal to x. So if you think of just plugging in some y values and doing this backwards, if we plug in y equals 0, what do we get? 2 to the 0 power is equal, or 10 to the 0 power, or any number for that matter to the 0 power was going to be 1. So we're always going to have that x-intercept at 1, 0, because no matter what y is, we're always going to get 1, 0 there. If we plug in 1, obviously, for the y value, we would get 10, because 10 to the first power, so is equal to 1. So our graph kind of looks like this for our common log graph. Let's go on to our exponential graph. Our exponential, remember, the base is e, so we're essentially taking e to the y power is equal to x, and if we look at that, if we plug in 0, as we said, we're going to get 1, so 1, 0 is on the graph. If we plug in 1, we get the base, and that's always going to be the case. Whatever the base is, 1 is always going to be a point on the graph, so natural base e is approximately 2.7, so 1 would be there, and there's our sketch of our natural base e for the natural log of x. So notice both those graphs have a vertical asymptote at x equals 0, goes through the point 1, 0, goes through the point whatever the base is, 1. And those are critical points whenever the base is greater than so whenever our a value is, when we're looking at this, whenever that base is greater than 1, that's going to be the case. When it's less than 1, it's actually not going to be increasing anymore. The graph is actually going to decrease. Now, it will still have a vertical asymptote at x equals 0. It will still go through the point 1, 0, but instead of increasing, it's going to be decreasing. So it'll look something along those lines if the base is less than 0. So this would be when a is less than 0 for our graph. You should now have enough to be able to complete the entire lesson. Tomorrow in class, we'll do some more examples with solving exponential and logarithmic functions, but this should give you a good start on being able to complete most of the assignment. Good luck.